Welcome to Chapter 11, Survival Analysis. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan. In many public health studies, we are interested in more than just whether an event happens. We care about when it happens. This chapter focuses on statistical methods for analyzing time to event data, especially when not all individuals experience the event during the study. First is Introduction to Survival Data. Survival data deals with the time from a defined starting point to the occurrence of an event. Common examples include time to death, relapse, or hospital discharge. A key feature is censoring. That means we don't observe the event for some participants during the study period. They may drop out or the study may end before the event occurs. Each observation includes time to event or censoring. An indicator of whether the event occurred or was censored second is estimating the survival function. The survival function, written as S and T in brackets, is the probability of surviving beyond a specific time t. It starts at 1 and decreases as events occur. We estimate it using the Kaplan Meier method. At each time an event occurs, we multiply the previous survival estimate by the conditional probability of surviving past that time. This creates a step function survival curve. Censored observations are marked on the graph but don't cause a drop. The median survival time is the time at which the survival probability reaches 0.5. Third is comparing survival curves. To compare survival between two or more groups, we use the log-rank test. It tests whether there is a significant difference between Kaplan-Meier curves. It does this by comparing the observed versus expected events in each group at every event time. This test assumes that hazards are proportional, meaning the risk is consistently higher or lower in one group over time. If the p-value is less than 0.05, we conclude that the survival experience is significantly different between groups. Fourth is Cox proportional hazards regression. The Cox model is a regression method for analyzing time to event data. It models the hazard, which is the instantaneous risk of the event occurring at time t. The model estimates the effect of predictor variables using hazard ratios. The hazard at time t equals the baseline hazard times the exponential of the sum of the coefficients times their variables. That means h in bracket t equals h naught of t times e to the power of b1 times x1 plus b2 x2 and so on. We don't need to estimate the baseline hazard itself to interpret the hazard ratios. Exponentiating the coefficients gives us hazard ratios. A hazard ratio of 1 means no effect. Greater than 1 means increased risk. Less than 1 means reduced risk. Fifth is extensions. Survival analysis can be extended in several ways. Time-varying covariates. Some predictors, like blood pressure, may change over time. These can be incorporated dynamically. Stratified Cox models, used when the assumption of proportional hazards doesn't hold across all groups. Stratification allows for different baseline hazards. Competing risks. Sometimes participants may experience different types of events. In such cases, we model the probability of a specific type of event using cumulative incidence functions. These extensions help make survival models more realistic and flexible. Survival analysis gives us tools for understanding not just if an event occurs, but when. We covered time to event data and censoring, Kaplan-Meier survival curves, log-rank test to compare groups, Cox proportional hazards models and hazard ratios, extensions for time-varying variables and competing risks. These tools are crucial in public health research where timing matters. This concludes Chapter 11, Survival Analysis. This video content is based on Essentials of Biostatistics in Public Health by Lisa M. Sullivan.